Yeah. So welcome back students. So good evening to all of you. So this is basically applications of thermodynamics part 2 ISRO PYQ का. So last time जब हमने वो सेशन किया था उसका काफी अच्छा रिस्पॉन्स आया था. So इसलिए हमें इस applications of thermodynamics का part 2 भी कर रहे हैं अभी. Okay. And last time we because of some time constraint we could not solve many of the questions. Actually, good evening Ashi. So जो क्वेश्चंस हमने लास्ट सेशन में नहीं किया था वो क्वेश्चंस हम इस सेशन में सॉल्व करेंगे. ठीक है. सो वेलकम ऑल ऑफ यू. सो प्लीज टाइप इन द चैट बॉक्स. Have you all, yeah, good evening again. So shall we continue with this session? So please type in the chat box. This is applications of thermodynamics part 2 actually here. Okay. So good evening all of you. So let us start solving these questions actually. Which of the following statements is true for Rayleigh flow? Okay. So Rayleigh flows at Mach number is equal to 1 basically here. Okay. So Mach number is equal to 1 is like last time also you're asking the transition basically subsonic flow से supersonic flow के बीच में actually Mach number is equal to 1 हो जाएगा. And now if you see what is the specialities of this Rayleigh flow. पहले Rayleigh flow क्या होता है? So let us study that. Rayleigh flow is like flow in a duct, 1D flow in a duct. फ्लो ऑफ आइडियल गैस जनरली जो सब्सटेंस फ्लो होते हैं वो हम आइडियल गैस कंसिडर करते हैं. सो 1D फ्लो ऑफ आइडियल गैस इन ए डक्ट नॉर्मली इन ए क्रॉस सेक्शन इन एनी डक्ट इन जनरल विथ हीट ट्रांसफर एंड नेग्लिजिबल फ्रिक्शन एंड नेग्लेक्टिंग फ्रिक्शन. इस स्टेटमेंट का मतलब क्या होता है? अगर हमने इस मतलब इस डक्ट फ्लो का एनालिसिस करके टाइम पे एक्चुअली हम हीट ट्रांसफर कंसीडर करते हैं लेकिन हाइड्रोलिक दिस लॉस ऑफ द फ्लूइड बेसिकली ड्यू टू द फ्रिक्शन वो हम नेग्लेक्ट करते हैं. ओके. सो नाउ इफ यू टॉक अबाउट दिस स्पेशलिटी हियर लेट अस सी. Rayleigh फ्लो का ग्राफ बनाते हैं एक्चुअली फैनो कर्व्स. सो नाउ इफ यू सी आई वुड लाइक टू गिव यू सम डेटा क्योंकि इस टाइप क्वेश्चंस गेट एग्जाम आई मीन इस एग्जाम में हर साल रिपीट होते हैं जनरली. सो this is T versus S TS diagram actually. Now Mach number less than 1, Mach number equal to 1 and Mach number more than 1 इनका regimes होते हैं. जैसे हमको laminar turbulent का regimes होते हैं वैसा यहाँ कुछ regimes होते हैं actually. Okay. So let us suppose this is the temperature at any location for example and this is the specific entropy at any given particular location. So Rayleigh flow ऐसे आते हैं. So generally this is the curve of the Rayleigh flow. And now इस curve में कुछ important चीज है हमको सीखने के लिए. इस point को ये and इस point को B अगर बोला तो so यहाँ dt by ds at this location A 0 होते हैं and यहाँ ds by dt क्योंकि यहाँ slope बहुत perpendicular था so ds by dt at B is equal to 0 क्योंकि यहाँ अगर tangent ड्रॉ किया तो this slope of the tangent will be 0 and slope of the tangent will be 90. and मैंने डिटेलली एनालिसिस नहीं कर रहे हैं अभी लेकिन आप अगर this analysis if you do you will understand certain points that this Mach number at which you get this इस लोकेशन पे Mach number का वैल्यू होता है कि Mach number is equal to square root of 1 by gamma actually here. Okay. So gamma is adiabatic index of this ideal gas. Adiabatic index of ideal gas. मैं अभी डेरिवेशन नहीं कर रहा हूं लेकिन इस ग्राफ का सारी इंपॉर्टेंट चीज आपको पढ़ाता हूं. ठीक है. सो दिस इज Mach number इज इक्वल टू स्क्वायर रूट ऑफ 1 बाय रूट गामा और कुछ बुक्स में 1 बाय स्क्वायर रूट ऑफ गामा बोथ आर सेम क्योंकि स्क्वायर रूट ऑफ 1 ही हो जाएगा. सो हियर Mach number एट दिस लोकेशन इज बेसिकली Mach number इज इक्वल टू 1 एक्चुअली हियर. ओके. मैं इस वैल्यूज 1 बाय रूट गामा यहां वैल्यू 1 कैसे होगा इनका डेरिवेशंस नहीं कर रहे हैं लेकिन you can slightly remember for this time because जब हमको मौका मिलता है डिटेल्ड एनालिसिस करने का जब मैंने आपको एप्लीकेशंस ऑफ थर्मोडायनामिक्स पढ़ाते हैं यूट्यूब में उस टाइम पे मैं आपको डिटेल्ड एनालिसिस देता हूं लेकिन अभी के लिए सो प्लीज रिमेंबर दीज वैल्यूज. इसका Mach number 1 by root gamma हो जाएगा एंड यह Mach number 1 हो जाएगा. ओके. एंड नाउ इफ यू सी गुड इवनिंग सौम्यदीप एंड मान लो कि दिस इज द कर्व एक्चुअली दिस इज द रेजिम टोटल. नाउ व्हेनेवर यू सी outside this Mach number is less than 1 and this is actually for cooling. Along this direction, these are the cooling curves actually, and heating is in this particular direction actually here. Okay. So normally compressible flows ISRO exam के लिए एक बहुत important chapter था, and I was telling that if you have time, डेफिनेटली आपकी इसरो की प्रिपरेशन के टाइम पे डेफिनेटली कंप्रेसिबल फ्लोस इस टॉपिक पढ़ के जाओ, ठीक है. सो कंप्रेसिबल फ्लोस, एंड आई विल आल्सो रेफर यू वन गुड बुक एक्चुअली टू फॉलो दिस थर्मोडायनेमिक्स बाय सेंजल. इस बुक में इस चैप्टर जरूर पढ़ने के बाद ही एग्जाम के लिए जाओ, ठीक है, क्योंकि हर ISRO के पेपर में इस चैप्टर से डेफिनेटली एक क्वेश्चन मिलेगा आपको, ठीक है. सो दिस इज कंप्रेसिबल फ्लोस ऑफ सेंजल. नाउ यू कैन सी दिस इज हीटिंग, this is heating actually in the direction of heating, and this is also heating, and these are the directions in the directions of cooling, and this is also basically cooling. And here Mach number will tend to infinity, Mach number बहुत बढ़ेगा, and यह Mach number 0 almost, okay. So इस cooling के केस पे Mach number will be almost, this will be tending to 0 in this locality actually, okay. So ये सारी चीज important रख लीजिए क्योंकि this question is completely related to this. Now in this Rayleigh flow, so this is the graph generated for Rayleigh flow. Rayleigh flow. Now in this Rayleigh flow, जब Mach number 1 हो जाएगा, when Mach number is equal to 1, so what are the points you can see? So this Rayleigh flow is for this ideal gas, you know. This is for the ideal gas. So ideal gas में एंथैल्पी सिर्फ टेम्परेचर में डिपेंड होते हैं, सिर्फ टेम्परेचर की फंक्शन में डिपेंड होते हैं आइडियल गैस होना तो. नाउ ट्राई टू अंडरस्टैंड वन थिंग, एट Mach number is equal to 1, इस पॉइंट में, so you can see इसी पॉइंट में what is the things that they are asking, let us see. Enthalpy is maximum. Tell me one thing, अगर आइडियल गैस का एंथैल्पी मैक्सिमम होना चाहिए तो टेम्परेचर क्या होना चाहिए? What should be the temperature if enthalpy has to be the maximum? It's an ideal gas, okay. So at ideal gas, if enthalpy has to be maximum, what should be the temperature? Temperature should also be maximum, correct? Yes or no? Type in the chat box. टेम्परेचर भी मैक्सिमम होना चाहिए, पर लेकिन अगर आपने इस ग्राफ देखा तो टेम्परेचर मैक्सिमम इस पॉइंट पे नहीं है, लेकिन इस पॉइंट पे है एक्चुअली, ओके. सो एंथैल्पी विल बी मैक्सिमम एट दिस पॉइंट ये एक्चुअली है, ओके. सो इस पॉइंट में एट बी वी डोंट हैव द मैक्सिमम एंथैल्पी क्योंकि एट पॉइंट बी टेम्परेचर मैक्सिमम नहीं है, ओके. सो देयरफॉर दिस स्टेटमेंट इज एक्चुअली रॉन्ग इन दिस केस. Entropy is maximum, बिल्कुल. So you can see this is the point where you have the ds by dt is 0. That means, sorry, this is actually, yes, ds by dt is 0 actually here. So therefore here in this case you can see whenever, even though there is a temperature change, this ds is basically 0. So ds is achieved a maximum value here, okay. So this value is S max, and correspondingly this value is T max. Of course if T maximum है तो this is also the location of H max actually here, okay. So entropy is maximum, this statement is true. Enthalpy is minimum, no, क्योंकि बहुत सारे पॉइंट्स होता है कि कहाँ टेम्परेचर इससे नीचे होते हैं, okay. So therefore this point is also wrong, so definitely both B and C are also wrong. So entropy is actually maximum at Mach number is equal to 1, and this concept is very very important. Normally the concept of normal and oblique shocks, please go to this chapter before going for the examination, clear, from that particular book Angel, okay. So please type in the chat box, are you all clear with this question? Everyone, so please type in the chat box, are you all clear with this particular question? लेकिन मैं इस ग्राफ का आपका डिटेल्ड एनालिसिस जब हमको मौका मिलता है उस टाइम पे मैंने आपको डिटेल्ड एनालिसिस करके कंटिन्यूटी इक्वेशन, प्रेशर एनर्जी इक्वेशंस लगा के आई विल एक्सप्लेन यू डेफिनेटली, बट लेकिन अभी टाइम थोड़ा कम है, सो इसलिए ये चार चीज आप सुनिए बस, ठीक है. नाउ लेट अस गो टू द नेक्स्ट क्वेश्चन. The degree of reaction in a axial flow compressor, basically any flow compressor, is defined as the ratio of static enthalpy rise in the rotor to static enthalpy rise in the stator, static enthalpy rise in the stator to static enthalpy rise in the rotor, rotor to static enthalpy rise in the stage, of course stator to static enthalpy rise in the stage actually. So degree of reaction क्या होता है? So आप सबको पता है कि जनरली हमको फ्लूइड मिलता है, so उस फ्लूइड को दो टाइप्स ऑफ एनर्जीज होते हैं, है ना, प्रेशर एनर्जी and also kinetic energy. Kinetic energy. Now depending on the availability of the pressure energy at the inlet, we define a quantity called degree of reaction actually. Degree of reaction, normally इसको R से हम डिनोट करते हैं actually. So this is equal to change in static head, static, or generally sometimes we call this pressure head. In rotor, it's about standard definition था सारे turbo में divided by total change in head in the stage. Total change in head in stage. In stage. मान लो कि state 1 to state 2 if you are compressing, then in this complete compression we will have some part of the compression because of this change in pressure head, and total compression is basically there. So this ratio is called degree of reaction actually here. Okay, so therefore you can see change in static enthalpy rise in the rotor. So these two are in status, so this is actually wrong. So ratio of static enthalpy rise in the rotor to static enthalpy rise in the complete stage actually. Okay, so this is not in the stator, but this is actually in the complete stage. So this is what we have. Change in total change in head, of course. Static head, you can say static head, of course. We mean only static head in rotor by total change in static head. Basically the pressure conversion in stage actually. So out of this total stage, whatever is the part that is in the rotor, that will define as this degree of reaction. And जो machines impulse machines होते हैं, normally impulse turbines and all, so उसके case में this value will be 0 actually. Degree of reaction is equal to 0 in that case. लेकिन कुछ degree of reaction turbines होते हैं like Francis turbine, Kaplan turbine, and normally in case of compressors and all, we have this value of R changing from 0 to 1 actually here. Okay, so generally this range of R theoretically is 0 less than R less than 1 actually, and change in static pressure head in the rotor divided with total change in static head within the complete stage of compression. Okay, and here definition turbines this is even same in the case of turbines as well. Clear? So therefore this value is C. Option C is actually correct answer in this case, because this is the exact definition in this case actually. Okay, so rotor to static enthalpy is actually wrong, but rotor to static enthalpy rise in the complete stage is what we will consider in this definition of degree of reaction. And this definition is a very common and standardly asked definition in all the turbo machinery problems and all. Okay, clear to all of you? Shall we go for the next question? So type in the chat box, everyone. So please type in the chat box. Is this clear to you so far? Vijay, Akhil, Soumyadeep, Rishi, Abhijit, Kiran, every one of you. So type in the chat box. Clear? So let's go to the next question. How does C10 number varies with octane number in fuels in IC engines exclusively? Okay, so 2017 में question आया था. So we have for any fuel actually we have two very important properties. One is called the octane number and one is called the C10 number. Okay, so what is this octane number and what is C10 number? Out of these two, which is of more importance, which we try to increase actually. Okay, so मैं आपको थोड़ा सा introduction देता हूँ, क्योंकि जब मैंने HPCL में काम किया था उस टाइम पे fuels पे बहुत ध्यान दिया. So normally if you take fuel, this has two numbers, of course, C10, octane number first. We'll talk about octane, one of the powerful, and C10 numbers. C10 numbers. Now what is this octane number? Basically is octane number decides the quality of the fuel in terms of pre-ignition. Like for example, you can see this is comparison or measure of pre-ignition. Measure of pre-ignition. Pre-ignition. Normally pre-ignition क्यों होता है? मान लो कि आपके पास एक piston cylinder का setup था. So whenever you have this piston cylinder assembly, okay, fine. Let us see. It has valves also. Fine. Let us keep some valves. Inlet valve, outlet valve, and also a spark plug. Now, let us suppose the piston is somewhere here, for example. So this is piston. And bottom you have the crank, all these things. So crankshaft, ये सारी चीज है. Okay, so crank, everything is there. Now, in the beginning of the compression stroke, when the piston is at the bottom dead center, when it moves to the top dead center finally, meanwhile you can see if the octane number of the fuel is low, अगर मान लो कि fuel का octane number थोड़ा कम है, उस टाइम पे क्या होता है? When octane number of the fuel is low, you will have small pockets of fuel getting segregated actually. Okay, so the fuel under this high pressure, because when the piston is moving, immediately the pressure inside the cylinder बढ़ेगा. So when this pressure increases, we have some small formation of fuel pockets. इनको बोलता है कि fuel pockets actually. And when you have this fuel pockets, this local fuel pockets will cause some pre-ignition actually. Okay, so by adding certain additives or by making some adjustments in the combustion ratio, you have to avoid this pre-ignition actually. Okay, so if to avoid pre-ignition, or basically what happens if there is a pre-ignition? Engine knocking, that knocking sound will come. So therefore this engine knocking will be there in case of pre-ignition. So engine knocking will be there. To avoid this pre-ignition or engine knocking, octane number has to be increased. Octane number has to be increased actually. Now what does this C10 number do? C10 number, C10 number is measure of delay in ignition. Delay in ignition actually. Okay, so this is delay, measure of delay in ignition. Normally this is about the pre-ignition and this is about the delay in the ignition. Now whenever there is a delay in the ignition, what happens? Maximum your power comes down. But ideally अगर इंजन efficiently काम करना है तो ignition time पे होना चाहिए. जब इसका spark plug जलाते हैं उस time पे सारे ignition we have to make sure that complete ignition happens there. Now what happens here is, let us suppose to improve quality of the fuel, हम क्या करना है? इसको बढ़ना चाहिए. So octane number has to be increased. Octane number should be increased. And since C10 number is the measure of delay in the ignition, so अगर delay कम करना है तो C10 number को भी थोड़ा कम करना है. Correct? So C10 number has to be decreased. C10 number has to be decreased actually in this case in IC engines. Now whenever you are increasing the octane number and you are decreasing the C10 number, because you don't want pre-ignition to happen, you want this octane number, you want the fuel to go till this point without ignition, and also you don't want any delay in the ignition. Okay, जब piston इस time पे होता है, then definitely you have to have the combustion. Okay, so therefore this C10 number should be low. There should not be any lag in the ignition and also there should not be any pre-ignition. So can you tell me the relationship between these two? If octane, for the quality of this fuel, octane number should increase and C10 number should decrease actually. Okay, so then tell me what could be the relation between these two for the performance of this fuel. How does C10 number varies with octane number in fuels in IC engines in general? Now looking at these options, so please tell me what we can do actually, how we can actually relate these two quantities. One number has to increase and one number has to decrease for the best performance of the fuel. So if one number has to increase and one number has to decrease, then out of these relationships, what relation is actually correct? Everyone, just think and tell. Okay, so for the better performance of this fuel, one number has to go up and एक number नीचे आना चाहिए. So अगर एक number ऊपर जाए and एक number नीचे जाए तो इन दोनों का difference मतलब relation क्या होता है? They are inversely proportional to each other actually. Okay, this is inversely proportional to each other. Octane number and C10 number. The delay should be minimized and pre-ignition should be avoided. Okay, so that's why this is actually inversely proportional to each other. Clear? So all of you type in the chat box. Arpit, Mani, Akhil, Vijay, Soumyadeep, Rishi, Abhijit, every one of you. Type in the chat box. Clear? So it is clearly C with a basic understanding. That's it. Okay, so C is basically the correct answer after this much of understanding actually. Okay, so normally in olden days what we have the additives to manage this knocking. Octane number बढ़ने के लिए हमें एक additive use करते हैं, उसका नाम होता है कि TEL. Okay, but लेकिन बाद में इनका experimentation and all they gave the results that TEL is very harmful to lungs of humans. Okay, जब हम fuel के साथ TEL mix करके इंजन में चलाते हैं उस टाइम पे थोड़ा dangerous gases release करते हैं इंजन से, so they are very dangerous for humans. So that's why this TEL, tetraethyl lead, which is once upon a time it was a very famous anti-knocking agent, but right now it was not used actually at any location. Okay, so that's why you can see this to improve quality of this fuel, we generally nowadays we go for hybrid engines, and also this combustion ratio manipulations is what we will do. Normally we have VCR engines, if you remember, variable combustion ratio engines. Depending on the type of the fuel, you can manage the combustion ratio. You can adjust the combustion ratio of the engine. Okay, so these are the things. Now let us see, in an ideal gas turbine cycle with intercooling, reheating and regeneration, as the number of combustion and expansion states are increased, which of the following statements are correct? The Breton cycle reduces to Ericsson cycle. The Breton cycle reduces to Stirling cycle. The cycle efficiency becomes equal to Carnot cycle efficiency. So out of this, which statements are correct? So जब हमने last time Breton cycle discuss किया था, उस time पे Breton cycle का TS diagram भी discuss किया. So let us go with the TS diagram. TS diagram. Normally वो जो Breton cycle होते हैं, if you see, that will have a combustion, or normally PV diagram, if you go for PV diagram also, not an issue, better PV diagram because you might be comfortable. It's Stirling and Ericsson cycles. So if you have P versus specific volume diagram, so first stage, isentropic combustion. One to two. Then, or basically you can see, if you try to do analysis with the help of Carnot cycle, then combustion is isentropic, expansion is also isentropic, heat addition is at constant pressure, heat ejection is also at constant pressure, correct? So this cycle will look something like this: constant pressure heat addition, then isentropic expansion, and constant pressure heat ejection actually here. Okay, so this is constant pressure heat ejection. So this is isentropic combustion, constant pressure heat addition, isentropic expansion and constant pressure heat rejection. So इसका TS diagram भी बनाते हैं हम. So TS, अगर आपने TS diagram भी बनाया तो देखिए क्या होता है. TS diagram. So पता है कि isentropic combustion 1 to 2 actually. Okay, so मैं diagram को थोड़ा सा यहाँ लाता हूँ. ठीक है. So 1 to 2. Then this is constant pressure heat addition, isentropic expansion. Whenever guys, यहाँ एक पॉइंट इंटरव्यूज के लिए बहुत इंपॉर्टेंट है. जब लोग ने आपको पूछता है कि टीएस डायग्राम बनाते हैं, उस टाइम पे 0.4 0.2 से ज्यादा मतलब ऊपर होना चाहिए. ओके, सो इट शुड बी एट ए हायर टेम्परेचर. T4 शुड बी ऑलवेज ग्रेटर देन द T2, क्योंकि कंप्रेशन के बाद जो टेम्परेचर होते हैं उस टेम्परेचर एग्जॉस्ट गैस का टेम्परेचर से नीचे होते हैं. ओके, सो देयरफॉर T4 शुड बी ऑलवेज मोर देन दिस T2. ओके, सो जब आपने डायग्राम बनाते हैं उस टाइम पे ध्यान रख लो कि 0.4 विल बी मोर और विल बी अबव दिस T2 एक्चुअली हियर. ओके, एंड देन you have a constant pressure combustion 4 to 1. These are at constant pressures. Now tell me one thing, whenever you are doing reheating, okay, let us suppose you are doing reheating and also regeneration, and you are increasing the number of stages of combustion and expansion. For example, okay, you know that this is the combustion and this is expansion, and you are doing lot of reheating and also regeneration, then this cycle will get converted as, look, will convert as P or T? Yes. Now this 1 to 2, which was initially this isentropic combustion actually. So your Hindi is almost in ICU. Yes, I understand, because I'm trying to speak. So but I hope you can understand the things actually. Okay, what I'm trying to convey, you're getting those things, correct? Okay, fine. So let us see this. Whenever you take this TS diagram, whenever you are increasing the combustion stages, normally you do the combustion in this way, correct? So combustion, then intercooling, then again combustion, then intercooling, again combustion and all. So whenever you try to closely pack all these things, then you will see, you will generate some curve like this, okay? Then whenever you are doing reheating, normally what you do, once you expand, then again you will go for reheating. Again you expand, again you go for reheating. Again you expand, again you go for reheating. So whenever you increase the stages, this will be almost like this line, and again this. Finally here also you will have this kind of lines actually here. So you can understand this process, which is actually the heat addition process 2 to 3. So that comes out to be something around like this, which is the heat addition here in this case, and this is the heat ejection. And here this will be almost like isothermal case. And these things, since you are doing at this constant pressure actually, so these things will be almost like the constant pressure curve in the TS diagram, and this becomes P is equal to constant in general. Okay, so this becomes P is equal to constant, and whenever you talk about this Berton cycle in actual case comes out to be Ericsson cycle actually here. Okay, so this becomes an Ericsson cycle, but not Stirling cycle, because in Stirling cycle you have the constant volume, heat additions and rejections, but here you can see this is actually Ericsson cycle. Okay, so we have statement the Berton cycle reduces to Ericsson cycle actually here. So this statement 1 is correct. Then what about statement 2? This do not come to be a Stirling cycle, so statement 2 is actually a wrong statement. So statement 2 is actually wrong. So this option is actually wrong. The cycle efficiency becomes equal to Carnot cycle efficiency. Now if you compare Stirling, Ericsson and also Carnot cycles, the temperatures of heat addition TH and TL remain same. So therefore the Carnot efficiency is same as the Stirling efficiency, is also same as the Ericsson efficiency. So therefore the cycle efficiency becomes theoretically equal to the theoretical cycle value, which is the Carnot cycle efficiency actually. Okay, so statement 1 is actually correct. Statement C basically 1 and 3 are actually correct. This Berton cycle will reduce to Ericsson cycle, and also the cycle efficiency becomes equal to this Carnot cycle efficiency, because whenever the cycle becomes converted to Ericsson cycle, Ericsson, Stirling and Carnot all three have the same efficiencies, because they operate under the same temperature range of constant temperature heat addition and also constant temperature heat rejection actually. So therefore this statement 1 and statement 3 becomes correct. Statement 1 and statement 3 becomes correct actually. And I have told you about one book, 𝐂𝐚𝐭𝐽. This book has the exact data of this statement actually, because काफी time मैंने applications of thermodynamics पढ़ाया था उस time पे. I can see that the same statement in the same order in an ideal gas turbine cycle with intercooling, reheating and regeneration, as the number of compression and expansion states are increased, then the cycle approaches to be Ericsson cycle, and theoretically the efficiency of the cycle becomes equal to the Carnot cycle efficiency actually. Clear? So that's why statement 1 and also statement 3 are correct actually here in this case. Okay, as per this PV and this TX of the Bertons. And under regeneration and reheating, they become a constant pressure, compression basically, then constant temperature heat addition, constant pressure expansion actually here. This arrow I think we have made in the reverse direction. So this will be a constant pressure in this case, and this will be a constant temperature heat rejection actually again in this case. Okay, so therefore we have this particular graphs. Then let us go for this next question. A light plane flies at 720 kilometers per hour in standard air at an altitude of 1000 meters. Determine the stagnation pressure at the leading edge of the wing. Take P air is equal to stagnation pressure. They are talking about the stagnation pressure. So if you want stagnation pressure, last time I have already given you this data. So in this stagnation pressure, P stagnation is equal to P air plus half rho V square actually here. Okay, and whenever it is in standard air at an altitude of 1000 meters actually here. Okay, so it is flying at an altitude of 1000 meters. So P air plus half times of V square actually. So P air is how much actually here? P air is basically 9 into 10 power 4 Newton per meter square, and these options are in kilopascals. So let us convert this also into kilopascals. 90 kilopascals plus half times of rho 1.1 into V square. So what is V? 720 kilometers per hour. So if you convert that to meters per second into 5 by 18. So this is the value that comes out, but this value will be in complete SI units. It's not in kilopascals. To convert that to kilopascals again, we will multiply with 1000, because this value will be in just pascals. So to make that pascals to kilopascals, we are dividing with 1000. V square 720 into 5 by 18 actually here. Okay, so this value is 18 times cancels out this 4 times, and a 0 actually comes out. So 4 5s are 20. So this is 200 square actually here. Okay, so this is 200 square. So if you simplify this, 90 plus half times of 1.1 into 4 into 10 power 4 divided by 10 cube actually. So this is the value that you have here. Okay, so if you simplify this, 10 cube will cancel this 10 power 4 10 times, and this will become 11 directly here. Okay, and 2 will cancel this 2 times. So 90 plus 22 gives you 112 kilopascals actually here. 112 kilopascals is what you have here. Okay, so 112 kilopascals plus this is flying at a height of 1000 meters. There is also some potential energy, right? So this complete energy will get converted to PS. So 112 kilopascals, yes, correct. So 112 kilopascals is actually the correct. If it's at 1000 Kelvin, they're asking at the same location, right? At the leading edge of the wing. Yes. Whenever it is flying at an altitude, even at the leading edge, potential energy will be same. So 112 kilopascals will be the correct answer in this case. Because if flight is flying at this height, then definitely its leading edge of the wing somewhere here, this will also be at the same height. Okay. So whenever the air molecules which are coming is at this potential head Z1, definitely by the time it is about to hit this, here also this value is Z2. So potential energy, even though you are bringing adiabatically, the potential energy will remain same. So therefore 112 kilopascals is actually the correct answer in this case. Clear to all of you? Is this question clear? Last time मैंने आपको इस equation भी दिया था. So please type in the chat box. Is this clear to all of you? Is this calculation clear? Can you understand? Because some people will add this potential energy term also. 9.81 into 1000 by 1000 is what they'll do, and they'll add this 9.81 to this 112, and they find that the answer is not given. We cannot add this potential term because whenever here at this point, when the flight is flying at some height Z, let us say, whenever this air stream, whenever it's coming at this potential height Z1, finally when it's hitting the leading edge also, when it's coming to be a locally stagnation point, this point is called stagnation point. So whenever this is coming to the stagnation point, even then in that case you can see this value will still remain at the same height actually here. Okay, so that's why potential energy should not be added. Clear to all of you? Did you understand why that 1000 you should not consider? Because there could be some idea to some people that we can also add plus GZ by 1000 actually. Okay, but that will give you a value which is equal to around 121 point something, which you cannot find here, because you should not add that 1000. Okay, because whenever this particle is at a height of Z1, when it is hitting the leading edge of the wing, then also the particles will be at the same height. Okay, is this clear to all of you? So type in the chat box, is this clear? Now let us go for the next question. A re-entry module flies with Mach number 10 at an ambient temperature of minus 27 degrees Celsius. So basically what are re-entry modules? Normally if you see space, we have some re-entry space flights again. So with Cp is equal to 840 joule per kg Kelvin, gas constant R is equal to 140 joule per kg Kelvin. What is the stagnation temperature at the tip of the nose of the re-entry module basically? Okay, so let us suppose this is atmospheric. Okay, then whenever the flight is entering here, basically, whenever the flight is entering here, at the tip of the nose, then definitely the air at this location will be stagnant point, because whenever the body is coming here, air will try to flow like this. So this point at the tip of the nose means somewhere here, here you have the nose. So at this point, it will be like the stagnation point in that case. Okay, so whenever that's the stagnation point, then what is the temperature, stagnation temperature at the tip of the nose of the re-entry module actually? Okay, so let us calculate what is the tip temperature. I have already given you the Ts is equal to T infinity plus V square by 2 Cp last time, correct? You remember this value? I have also given you some slides in between how this formula is coming. Do you remember that? Yes or no? Type in the chat box. So type in the chat box, I have given you this expression. Do you remember this expression? Yes or no? I have also given you some slides and told you that this is very important for ISRO. You can see every year almost there is a question on that particular stagnation property, stagnation temperature, stagnation pressure, all. Whoever has attended the last session, definitely वो लोग को पता है, मैंने आप सब लोग को ये formula दिया था. Okay, now Ts is equal to, so this is the stagnation temperature, T infinity plus V square by 2 Cp. Now here Mach number is given to you. So what is Mach number? Mach number is equal to V by A. So V square can be written as acoustic velocity square into Mach square actually. Okay, so this is Mach number square actually. Okay, so this is Mach number square. Now what is the expression for acoustic velocity? I have given you that also, calculation of acoustic velocity, which is equal to square root of gamma RT, of course. Okay, so A is equal to square root of gamma RT. This is the expression for the acoustic velocity. Last time जो मैंने आपको PPT दिया था, उस PPT में सारे derivation है इसमें. Okay, so A is equal to square root of gamma RT. Now if you see this, Ts plus is equal to T infinity plus V square is nothing but this is of course T infinity at that conditions. So at the same condition of the ambient. So square root of gamma T. So V square can be written as A square into Mach number square. So what is the A square value? Gamma times R T infinity into this Mach number square. ma square by 2 times of Cp. So we can write Cp as gamma r by gamma minus 1 again. Okay, so we can write this Cp as gamma r divided with gamma minus 1. So when you cancel these terms, gamma r and this gamma r, when you cancel, so this is equal to Ts is equal to T infinity is common in both the terms. So T infinity times of 1 plus this gamma minus 1 is in the denominator of denominator. So that can go to the top. So max square into gamma minus 1 divided with 2 is what you have the final expression in this case. Okay. Now let us take the values. T infinity. So T infinity is how much? T infinity. Let us check. T infinity is equal to, so what is the temperature of this module at this time? At the ambient temperature of minus 27 degrees Celsius. So minus 27 degrees Celsius. So 273 minus 27 actually. So if you see this expression is 6, then 6 minus 2, 4, 246 actually. So 246 Kelvin. So what about this Mach number? Mach number is also given. This flight is entering with a Mach 10 actually. Okay, so Mach number is equal to 10 of course in this case. And what about this gamma? So gamma is equal to Cp by Cv. So let us see what is the value of Cp they have given you. Cp is 840 joule per kg Kelvin. So 840 divided with Cv. So Cv का value क्या होता है? Cv is equal to Cp minus R. Okay. So Cp is 840 minus R value is 140. So this is equal to 700 kilojoules per kg. So this is 700 kilojoule per kg. So 700 kilojoule per kg. So this is the value of gamma actually here. Okay. So you can see this value is 1.2 almost. Okay. So 700 because 0 gets cancelled. 84 by 7 is 12. So 12 divided by 10, 1.2 actually here. Okay. Okay. So this is, okay. Thank you, Dhamve Singh. So see here, this is 1.2 actually. So gamma value is 1.2. When gamma is 1.2, then this implies, so आपके पास सारे चीजों का values है. So Ts is equal to T infinity, which is 246 Kelvin multiplied with 1 plus Mach square. So what about this Mach square? Actually, Mach square is 100 because Mach number is 10 into gamma minus 1, 0.2. Gamma is 1.2, so gamma minus 1 is 0.2 divided with 2 actually here. Okay, so this is divided with 2. Now if you simplify this, this is 0.1, so 1 0 can be cancelled. So 246 times of 11. This is in Kelvin actually here. Okay, so 246 and 246 actually. So this gives you 6, 0, 1. This is 7, so 2. 2706 Kelvin. 2706 Kelvin. Now if you see the options, this values are in degrees Celsius. Okay, so if you calculate this in degrees Celsius, let us check. 2706 minus 273 actually here. So 6 minus 3, 3, 10 minus 7, 3, 6 minus 2, 4, 2433 degree, 2433 degrees Celsius. Around 2400 degrees Celsius is what you have here. Okay, so if you check the values, around 2477, you can say this is the closest value. So 2477 is what you can take. Okay, so 2477, because this calculation we have done exactly, but the value could be around 24 degrees Celsius. Normally this reflight, re-entry concept is very dangerous. You know, do you know about Kalpana Chawla ma'am? Actually, the first female astronaut from India. Do you know? How many of you know this? Yes? You know why she died or what happened to her? To the team, complete team actually. At that time, yes, died in rocket actually. Okay, so Kalpana Chawla ma'am is the first woman astronaut from India. She worked for NASA actually, National Aeronautics and Space Administration actually, NASA, the US firm. So whenever the re-entry module, so this question basically if you see, the re-entry module is entering the earth and you can see that level of temperatures actually. Okay, so 2433 at that level. So at that level, the thing got, basically the re-entry module got fire and it got blasted up actually. Okay, and all of them lost their lives because this is the temperature range at which it enters the earth. Okay, sometimes at this high temperatures, it catches fire very easily because of the friction between the air molecules and the plane. Clear? Whenever things are hot, it's very easy for you to catch fire. Okay, so things like that. Around 2400 degrees Celsius. So this you can round off accordingly. Okay, fine. So please type in the chat box. Is this question clear to all of you? This calculation and everything. Okay, Arpit, Akhil, Vijay, Damvi, SK, lot of you. Okay, fine. Now let us solve the next question. Critical to stagnation pressure ratio P star by P naught for an expansion process is dash. Actually 2016 ISRO mein aaya tha. So now if you see this, look, normally there are two important things you have to note. One is stagnation properties and one is critical properties. Critical properties. So stagnation is known to you. Whenever you bring the local velocity of the fluid to 0, then what are the properties of the substance? At that condition, that value is given by this stagnation properties. Critical properties. Whenever you have a converging diverging nozzles, generally, this location is called throat, of course. So this is called throat of the nozzle. And here if you see, this location has Mach number is equal to 1, which is very critical to handle. Okay, you will learn why it is critical to handle. Agar aapne compressible flows mein ek detailed course liya to, you will definitely come to know why this Mach is equal to 1 is very tough actually. Okay, so whenever this Mach is equal to 1, then in that case you can see whenever this Mach number is actually equal to 1, that properties at that particular situation is called the critical properties. Okay, so this state corresponds to Mach number is equal to 1. This state corresponds to velocity is equal to 0. Whenever complete fluid is brought to rest adiabatically, whatever the properties are there, those properties are called the stagnation properties actually here. Okay, so now if you see this, the ratio, this actually the derivation I cannot do right now because I have to start with the continuity equation and also the energy balance, steady flow energy equations of this nozzle and all. So right now I am not doing that part, but I am just giving you values. Here these values are denoted by the subscript S or sometimes not actually. Okay, so PS or P naught, TS or T naught. Similarly, one very important thing that comes is density, stagnation density or stagnation not actually. So this is how they are denoted. Here they are denoted with P star, this T star and also density star of course. Okay, density star. Now whenever you see these values, you will see P star or T star, basically T star divided by T naught. Critical temperature to stagnation temperature. This value will be 2 by gamma plus 1 actually here, depending upon the type of fluid. Okay, this analysis is not very simple. You have to do a bit of mathematics and steady flow energy equations, continuity equations and all to derive this, and taking that Mach number is equal to 1 in the formulas and all. But right now I am just giving you this. T star by T naught is giving you 2 by gamma plus 1 actually here. Okay, and P star by P naught is equal to 2 by gamma plus 1 whole power gamma upon gamma minus 1 actually here. Okay, so this is the value of critical pressure to critical pressure to stagnation pressure actually. Normally in case of boilers also you can study this, and also then in that case density star by density naught is equal to 2 by gamma plus 1 whole power 1 by gamma minus 1 actually here. Okay, so this is what you have, 1 by gamma minus 1. This is not characteristic gas constant, this is actually gamma in this case. Okay, so this is gamma. Here also it is gamma basically, because some of you may feel again this is looking like characteristic gas constant. So this value is in gamma actually. Okay, so 2 by gamma plus 1 whole power 1 by gamma minus 1. Okay, and definitely जब हमको मौका मिलता है उस टाइम पे मैंने सारी चीज़ों को एक्सप्लेन करते हैं. ओके, अगर मैंने एप्लीकेशंस ऑफ थर्मोडायनामिक्स कोर्स लिया तो उस टाइम पे सारी चीज़ वही यहाँ 2 by gamma plus 1, व्हाट इज द इंपॉर्टेंस ऑफ दिस 2 by gamma plus 1, ये सारी चीज़ मैं आपको पढ़ाता हूँ. ठीक है, फाइन. So, लेकिन for now please keep the values, but please remember whenever you bring a flow isentropically to static condition, this is local velocity is equal to 0. So this is the stagnation point. And any point in this regime is called the critical point actually, or critical regime basically here. Slightly Mach 0.99 to 1.01 is what we will take. So that regime is called the critical regime actually here in this case. Okay. So will you take ATD in Vijay batch? Yes, I'm going to take ATD, applications of thermodynamics, in Vijay batch. Okay. Now, so these are the things. And meanwhile, as I told you many times, if you have anything to discuss with me, you can always contact me at https://t.me/pw Vinay. So, okay, so you can follow this Telegram group actually. So whenever you have any issues or any sort of things to discuss with me, you can keep it there. Okay. And here you can always discuss with me thermodynamics, fluid mechanics, applications of thermodynamics, heat transfer, and also maths. Okay. Fine. So let us see this question. So this is the importance actually. I'm not doing these derivations right now. Kyunki derivations करने का बहुत time लगते हैं. So therefore we are just giving you the values actually here. Okay. So whenever you see this, now let us see what are the values. Here they have given you this with lambda. Lambda is basically this gamma is what in this case. Okay. So lambda is equal to gamma. So another representation. This is adiabatic index basically. Adiabatic index. Now, what is the ratio of this stagnation pressure to the critical to the stagnation pressure? Okay. So if you see P star by P naught is equal to this 2 will not be there here. Similarly, this lambda plus 1 by lambda minus 1, this is also wrong. So 2 by gamma plus 1 into gamma by gamma plus 1. No, this is also wrong. This is not plus here. So gamma by gamma minus 1. Yes, this is correct. Option D is actually the correct answer in this case. Okay. I'm telling you guys, ISRO के लिए compressible flows बहुत important topic है. Okay. And please study the topic before going for the exam. Definitely एक दो questions मिलेगा उससे. ठीक है? Fine. And also I suggest you to study thermodynamics, fluid mechanics, and heat transfer at a good level, so that whatever the questions come from there, definitely can 100% answer that. Okay. Kyunki engineering mechanics and strength of metals, these kind of subjects you might have seen the PYQs also. Normally, if you have some general basic idea, you can easily solve. But generally, these compressible flows or turbines, what I have discussed actually. So these topics, you don't look at those topics much in GATE examination. Okay, so please put some extra effort in those topics. Clear to all of you? Okay, so this is basically the things. Okay, and whenever we do for compressible flows, then definitely I'll show you the derivations of these ratios actually. Okay, last time जब मैंने ATT पढ़ा था काफी time back, then I have told all these topics, but right now I'm just giving you some data for now. Okay. So Seebeck effect. Seebeck effect is actually thermocouples. Okay. Not related here, but normally when you do the temperature measurement, Seebeck effect is based on the thermocouples, based on the metal differences and all. Okay. But there is some effect of back pressure and all in case of nozzles, compressible flows and all. So that right now we are not, because that's again very good concept and very lengthy concept also, like basically normal shocks and oblique shocks, all these things, shock waves and all we have to go, but right now we are not doing that actually. Okay. Now let us see this. Efficiency of a Carnot engine is given as 80%. If the cycle direction is reversed, what will be the value of the COP of the reversed Carnot cycle? So can you please tell me? So can anyone tell me what will be the value of reversed Carnot cycle actually? Good evening, Deja. So please type in the chat box. COP efficiency of a Carnot engine is 80%. 0.8. So what is the efficiency of reversed Carnot engine actually, or reversed Carnot cycle basically here? Do you know the relation between thermal efficiency, efficiency of a heat pump, and efficiency of a refrigerator actually? Do you know this? Let us suppose if there is a cycle which is running on Carnot cycle, for example, such that it is operating between some temperature limits actually. Okay. Then let us see. I'll again give you some data here quickly. If you have a temperature, for example, TH, which is actually supplying heat, which is source basically, it is supplying some heat to a reversible heat engine, basically a Carnot engine, let us suppose. So Carnot engine. And you also have a TL, a sink, basically, which is ejecting heat, to which heat is ejected actually. So let us suppose if this is QH, produces some work W, and this value is QL actually here. Okay, so this is QL. So QH, W, and QL. So thermal efficiency of this Carnot engine is of course 1 minus TL by TH. If you simply analyze this, TH minus TL by TH of course, and this formula whatever you have is nothing but the coefficient of performance of the heat pump which is operating within the same temperature limits with these two, with all these three directions, QH, W, and QL being reversed, because heat pump is a power consuming device actually. So whenever you reverse this heat work input, then definitely heat gets transferred from low temperature to high temperature. Okay, so therefore COP of this heat pump will be equal to 1 by thermal efficiency of this heat engine, reversible heat engine of course. Reversible heat pump is equal to, this is reversible heat engine, and this value will be equal to COP of the reversible heat pump is equal to COP of the reversible refrigerator operating within the same conditions plus 1 actually. Okay, so this relation is very important and time saving relation many times. So this is what you can keep. Okay, so in second law of thermodynamics, people might have shown you, because when you take absolute scale of temperatures, this thermal efficiency of the Carnot engine or reversible heat engine can be written like that. Okay, so this can be written as 1 by TH minus TL. So this is actually equal to the thermal, this coefficient of performance of the heat pump actually. So therefore, thermal efficiency of the heat engine is same as 1 by heat pump, or COP of the heat pump is actually equal to 1 by thermal efficiency of the heat engine, provided both this heat pump and reversible heat engine are reversible actually here. Okay, so therefore, this is the case. This formula is very, one of the very simply derived like this basically, and if you want to know that COP of the reversible refrigerator is TL by TH minus TL, so if you simplify again you will get this expression. That's why COP of reversible heat pump is equal to that values. Okay, so therefore let us see here, thermal efficiency of this is reversed Carnot cycle, reversed Carnot engine. So whenever the heat engine is reversed, it works as a refrigerator. So this is 1 by 0.8. This gives you the COP of this, COP of the reversible, normally we denote this with COP. So COP of reverse Carnot engine is 1 by 0.8 minus 1 actually here. Okay, so this is going to be the reversed Carnot cycle, normally reversed Rankine cycle, reversed Brayton cycle. All these are refrigeration cycles actually. So whenever you reverse this Carnot cycle, then 1 by 0.8 gives the COP of the heat pump, but since you want the refrigeration COP, so this is 1 by 0.8 minus 1 actually here. Clear to all of you? So is this clear to all of you? So please type in the chat box. Normally, whenever you reverse a reversible cycle, that operates as a refrigerator, because normally in case of heat engine, heat gets taken from the high temperature and delivers some work output and ejects to the low temperature. So whenever it is reversed, the principle becomes completely opposite. And you might have studied reversible Brayton cycle, or basically reversed Brayton cycle, which is also called the Joule cycle, or reversed Rankine cycle, reversed this Otto cycles. All these things, they produce the refrigeration effect actually. And 1 by 0.8 minus 1. So this is 10 by 8 actually, 1.25 minus 1. So this gives you 0.25. This is the efficiency of the refrigeration. Refrigeration actually. Okay, so 1.25 will be the COP. Understood? Clear to all of you? Is this formula clear? Because this, look, this is very simple. I can show you, but whereas the previous case, they are time consuming. So I am, forwarding that for the detailed course sometime later. Okay. So please type in the chat box. Is this clear to all of you? Everyone? Akhil, Ramani, Kiran, Vivek, Vijay, Tejas, Akhil, all of you. So type in the chat box. Is this clear to everyone till this point? So 0.25 is basically the COP of this refrigeration. Okay, then let us go for the next question. A refrigerator removes heat from a refrigerated space at minus 5 degrees Celsius at a rate of 0.35 kilowatts and ejects it to an environment at 20 degrees, the minimum required power input. Now tell me one thing, if the power requirement is minimum, then definitely the refrigerator should work under ideal conditions. Yes or no? If refrigerator is working under ideal conditions, then what could be the cycle? Basically, it's a Carnot cycle, reversed Carnot cycle actually. So therefore, whenever you have this refrigerator, you have this reservoir, also this reservoir, and also you have some reversed cycle which is operating here. Okay, so this is a reversed Carnot cycle. So let us say this is how much? 20 degrees Celsius, so which is 293 Kelvin. And this temperature here, so this is minus 5 degrees Celsius. So the cold space is minus 5, so 268 Kelvin actually. Now, whenever you supply some work, W dot, this is giving you Q dot H by receiving Q dot L from this space. And this is a anti-clockwise cycle because it is a power consuming cycle. Normally, if you see the direction of the cycles or the sense of the cycles, clockwise cycles are generally power producing cycles. You might have known this always, like Otto cycle, diesel cycle, dual cycle, Rankine, Brayton, everything, all these cycles will be in the clockwise direction. Okay, but let us suppose if you are doing refrigeration cycles, VCRS, vapor compression refrigeration, then in that case, definitely the cycle will be anti-clockwise because refrigeration cycles are actually power consuming cycles. Okay, so you can easily understand that from the basics of thermodynamics. Let us suppose you have PV, for example. Okay, let us suppose you are trying to create a cyclic process. 1 to 2 and 2 to 3, something like this. Now, let us suppose if you create the cycle in this direction, that means you can clearly understand from 2 to 1, volume is actually decreasing, so it's a compression, and 1 to 2, volume is actually increasing, so it's an expansion. So therefore, you can clearly understand this magnitude of work in the compression is less as compared to the magnitude of the work in the expansion process. So therefore, this whatever is not the common portion, that is the net work which is generated by the cycle. So therefore, you will have a clockwise direction. But let us suppose if the cycle is in the reverse direction, then definitely work required for the compression will be more, and the net cycle, the net work interaction in the cycle will be negative actually. Okay, so therefore you can actually write that all power producing cycles are in the clockwise direction. You can see Otto, diesel, dual, Rankine cycles, this Berton cycles, all these Stirling, Ericsson, all these cycles will be in the clockwise directions. Okay, but whereas when you talk about VCRs, vapor compression refrigeration cycles, they will be in the anti-clockwise direction because you will supply the work input to the compressor actually in that case. Okay, so anyway, 268 Kelvin. So let us see what they're talking about. The refrigeration removes this space at 0.35 kilojoule per second. So this is 0.35 kilowatts. Let us say kilojoule per second is nothing but kilowatts. Then what they're telling? The minimum required power input is dash watts. Okay, so power input, you know, coefficient of performance is equal to, this is a reversible cycle they have given you? No, they have not given you, fine. Then the minimum power, okay, so if this has to be minimum, then definitely the cycle has to be a reversible refrigerator, because in that case only this will be minimum, otherwise it will be something more than that minimum value. So since this is a refrigeration cycle, you know, COP of reversible refrigeration can be written as desired effect. So when you do refrigeration, your point of interest is this Q dot L divided by W dot actually is equal to TL, which is the low temperature out of these two, divided by the temperature difference. So this implies Q dot L 0.35 divided by W dot is equal to TL 268 divided by this difference. What is the difference actually here? 268 divided by what is the difference? Difference between these two, 268 and 295. So this is 293 and 268. So the difference is 25 actually. Okay, so this value is 25. So let us see, W dot is equal to 0.35 into 25 by 268 actually here, correct? So TL divided by TL minus TH minus TL. So this is 25, this is 268. 268 by 25 is equal to 0.35 divided by some value here. Okay, so then if you calculate these values, then the required power input, what is that value? 0.35 kilowatts. Okay, this is kilowatts. These answers are in watts. Fine. So if you multiply 1000 here, if you multiply 1000, then this value becomes watts, of course. Okay, so W dot is equal to some watts. But how to do this calculation? Look, try to understand one thing. Actually, you can do this calculation very simply. See here. This value, if you take this value, or basically this value, 25 divided by 268, this is almost equal to 1, correct? So this is almost equal to 0.1, slightly less than 0.1, slightly less than 0.1, almost some 0.09 of that range. So whenever this is of 0.09 of that range, this total value, the 0.35 into something slightly less than 0.1 will be slightly less than 0.35 actually. Okay, so that means around 33, 34 within that range. So if you do this calculation also, you will end up with 33 watts around. Okay, so if you want, you can see this is 350 into 25 by 268. Since calculator is not allowed, you can perform this calculations a bit simply. So this is 175 and this is 134, of course. Okay, so this value you can calculate 175 times of 25 divided by 134 actually. Again, some 5 tables or 6 tables, basically you can do some calculation, you will easily end up with 30. It will be definitely more than 30, okay, because it won't be that much less. So around 33 watts could be the correct answer. Are you all getting 33? If you have done the calculation, you will get easily. So type in the chat box 33 watts. Are you all getting this 33 watts actually here? So please type in the chat box this 33 watts. Is this clear to all of you? Okay. Yes. Because you can understand from this value also, this value will be slightly less than 0.1. Okay. So whenever this value is slightly less than this 0.1 actually, then this 0.35 into something less than 0.1 will be something close to 35 actually. Okay, so 34, 33.5 something could be there. So 33 watts could be actual approximation value actually in this case. Okay, 33 watts. Okay, so let's go to the next question. For the same combustion ratio, the thermodynamic cycles in the order of decreasing efficiencies are, means basically in the order of decreasing efficiencies actually. Okay, so let us see, whenever for same combustion ratio, definitely efficiency of auto will be more as compared to efficiency of dual, will be more as compared to efficiency of diesel. For same peak pressure, whenever the peak pressure is same, for same peak pressure, thermal efficiency of diesel will be more as compared to thermal efficiency of dual, as compared to thermal efficiency of auto actually here. Okay, so and here the comparison is between dual, auto and diesel cycles. Okay, you can show this thing mathematically and also with some bit of physical explanation actually. Okay, I'll try to do, look here. Let us suppose you have the PV diagram, for example. Okay, whenever this combustion is same, for the same combustion ratio, so let us suppose in both auto cycle and diesel cycle you have the same combustion ratio, 1 to 2 of course. So this is combustion. Now in this case of auto, you have a constant volume heat addition, but here you can clearly understand it's a constant pressure heat addition. Okay, so this is a constant pressure heat addition. Now whenever you see this curve comes something close like this, and this will end up at constant volume. Similarly here also, this curve, let us suppose if it's touching here somewhere here, then in that case also this will be the adiabatic isentropic expansion, and this will be the point actually. Okay, now in this case you can understand basically here this work generated is less, work of auto is basically less than, work of auto is actually more as compared to work of diesel. And what about the heat interactions actually, or you can write this expression in terms of 1 minus QR by QS actually here. Okay, now let us suppose whenever the combustion ratio is same, if this 2 is at the same, definitely in this case of constant volume heat addition, you can understand when the temperature of heat ejection is same, but the temperature of heat addition will be at a higher temperature considerably in the case of this auto cycle. Okay, because you have already increased the pressure to this point, and further that at constant volume you are increasing the pressure during the heat addition process. That means the temperature of heat addition in case of this auto cycle is going to be large for the same heat rejection temperature in both the cycles. Okay, so therefore we are telling you for the same heat rejection process 4 to 1, for this same heat rejection process actually heat rejection process is same in both the cases, but you can understand this value, heat is added at high temperatures. And normally as per your second law, if you see, thermal efficiencies is equal to 1 minus TL mean by TH mean. So you can understand this TH mean will be large in case of auto cycle. Okay, because after this point you are further increasing the temperature during the process of heat addition actually. Okay, so that's why this is the case. Okay, and you can see this is QS minus QR in case of auto will be more as compared to QS minus QR of diesel actually. And whenever you understand that the heat ejection process is same between the two cycles, then definitely Q heat supplied in case of auto is actually large in case of heat supplied. So therefore thermal efficiency is equal to 1 minus QR by QS. In this expression QR remains same, but QS is more for auto in general. So therefore efficiency will be definitely large for auto cycle at same combustion ratio. Okay, so similarly by taking graphical analysis you can talk about this diesel cycles also for the same amount of peak pressure. Okay, so whenever peak pressure is same, then definitely you will end up with this expressions that diesel has higher efficiency as compared to dual, as compared to auto. Mathematically how can you show this is, look, I'll show you how can you show mathematically. Thermal efficiency of diesel or auto 1 minus 1 by R power gamma minus 1, correct? And thermal efficiency of diesel is equal to 1 minus 1 by R power gamma minus 1 multiplied with rho power gamma minus 1 divided with gamma times of rho minus 1 actually here. Okay, so this is the value. And now if you try to simplify this, definitely you will find one thing, that this value is definitely greater than 1 actually here. If you use small bit of mathematics here, you will easily understand that this value is going to be more than 1, because whenever this is rho power something, actually rho power 1.4 something like that, whenever as rho tends to 1, your diesel cycle gets converted to Otto cycle. Otto cycle. What is the physical meaning of this? In this case, this, if this is 0.3 in this case here, you know, this is the heat addition process. 2 to 3 is the heat addition at constant pressure in case of Otto, this diesel cycle. So at constant pressure, whenever this cutoff ratio is tending to 1, cutoff ratio is actually equal to V3 by V2, right? So whenever rho tends to 1, this implies V3 is very close to V2, of course. Okay, so whenever V3 is very close to V2, you don't have enough movement of the piston, so this will be very small actually. Okay, so whenever this will be very small, that means volume change is almost very small. That means you can approximate the heat addition is at constant volume, which is the same principle of this Otto cycle. Okay, and also mathematically, if you apply L'Hospital rule, you will get this as rho tends to 1. Look, I will show you. As rho tends to 1, you can see limit rho tends to 1. I will show you mathematically here, some maths here. So limit rho tends to 1, rho power gamma minus 1 by gamma times of rho minus 1. So this will give you 0 by 0 form directly. Okay, because when you put 1 power gamma is 1, 1 minus 1, 1 minus 1, 0. So now if you apply L'Hospital, limit rho tends to 1, derivative of this term, gamma times of rho power gamma minus 1, minus derivative of 1 is 0 divided with this gamma, don't have any limit, so gamma times of derivative of rho is 1 actually here. So gamma and gamma gets cancelled. So when you put rho is equal to 1, this term, total term will be 1 actually. So whenever this term becomes 1, then the expression for diesel cycle will be same as the expression for the Otto cycle. Okay, so these are some important insights about the Otto and diesel cycles. So at some point, if you want to know, you can learn this. Okay, clear? So anyway, at same compression ratio, definitely this in the decreasing efficiencies. So highest will be Otto, then followed by dual, and then it will be followed by diesel actually here. Okay, so this is the order of decreasing efficiencies. So definitely you can see efficiencies are getting decreased in this case. So Otto will have the highest, followed by dual, followed by diesel cycle. Clear to all of you? Are you all clear with this explanation? What we have given here? So is this clear to every one of you? So please type in the chat box. Okay, so this is mathematically, and this is from the thermodynamics point of view, understanding here. Okay, so type in the chat box. Is this question clear to everyone? Every one of you. So please type in the chat box. Is this clear to every one of you? Clear? Fine. So let us solve this question. Stagnation temperature. Again, you see 2011. So the stagnation temperature of an isentropic flow, K is normally denoted with this gamma, 1.4 is 360 Kelvin. If the temperature is 200 Kelvin at a section, then the Mach number of the flow will be dash. Okay. So let us see what is the Mach number. This is of an isentropic flow of air. Gamma is given 1.4. So you know, see how many times we are writing this formula. Ts is equal to T infinity plus V square by 2 times of Cp actually. So Ts is equal to T infinity plus, we want Mach number. So if you want, this V square can be written as acoustic velocity square into Mach square divided with 2 times of Cp. So Cp, let us keep this Cp actually. So Ts is equal to T infinity plus A square can be written as gamma RT into Mach square divided with 2 times of Cp. So what about the value of Cp actually? Cp can be written as gamma R multiplied with gamma minus 1 of course here. Okay. So now if you simplify this case, let us see. Gamma R and this gamma R gets cancelled. So this is also T infinity basically at that particular conditions. So Ts by T infinity is equal to 1 plus Mach square into gamma minus 1 divided with 2. So this is the expression finally here. Okay, so this expression is basically some important expression again. So Ts by T infinity is equal to 1 plus max square multiplied with gamma minus 1 divided by 2 actually, because if you take T infinity common, then this is the term. Now they have given you gamma. Gamma is equal to 1.4. So gamma ka value is 1.4. So gamma minus 1 is 0.4 actually here. What about Ts? Ts bhi deta. So Ts ka value kitna hai? Stagnation temperature of the air is 360 Kelvin. So this is 360, and T infinity ambient temperature is 200 Kelvin at a section. So this is 200 Kelvin. So let us see what is the value of Mach number. Simple calculation. Let us do. So 0 gets cancelled. 2. This is 18. So 1.8 minus 1. 0.8 is equal to 0.4 times of Mach square by 2 actually here. So clearly you can understand this value cancels this 2 times. So Mach square is equal to 4. So Mach number is equal to 2 in this case here. Okay. So Mach number is equal to 2. Clear to all of you? So this Mach number value is basically 2 in this case. Okay. So Mach number is equal to 2. You see how many times I'm writing this formula? I'm telling you guys, in thermodynamics exclusively and also in applications of thermodynamics, the level of questions that's being asked here in the latest trend, at least from 2017, if you see, all these questions are, majority I can show you that these questions are from 𝐁𝐚𝐭𝐜𝐡. Okay, 𝐁𝐚𝐭𝐜𝐡 and Bowles. That's why in every thermodynamics class, every course what I start, in the first lecture, I'll tell you 𝐁𝐚𝐭𝐜𝐡 on Moyne and Sapir. Moyne and Sapir is more like for gate examination, you can say, because a lot of problems will be analytical and all, lot of calculations and all will be there. So this 𝐁𝐚𝐭𝐜𝐡 and Bowles is like one very excellent book where you keep on, it's like a story book also. Okay, I'm telling you, no terminologies will be complicated in 𝐁𝐚𝐭𝐜𝐡. Once you start reading the book, you can continue that till the end of the book actually. Okay, if you use little mathematical knowledge doing some derivations and all, that book looks very easy. Okay, nowadays you guys are smart enough to bypass all the securities and download a copy from internet, but I cannot show you. This is a live session, but you guys can try to get a copy of that. Okay, fine. But if you wish to pursue your, after engineering, if you want to leave your thermodynamics, of course, even if you leave, that won't leave you at many parts. But still, if you want to have some good knowledge on thermodynamics, try to have a copy, some hard copy, printed copy with you. Okay, 𝐁𝐚𝐭𝐜𝐡. And the best thing about this 𝐁𝐚𝐭𝐜𝐡 book is, why I keep this name so many times is because in 𝐁𝐚𝐭𝐜𝐡, whatever the values you have, for example, specific heat of iron, this much, specific heat of a potato, this much, normal, some examples will be like this. So all these values are real-time values, means what are the values you see in the outside, in actual cases, same values will be there. Okay, so that's why these books are very much important. Clear? Okay, and I know that this is going to be the last PYQ session, that is the free session on YouTube as far as I take. So that's why if you find, if you find some time, then you can again go through these questions and all. Okay, but I'm telling you guys, PYQs are the heart and what do you say, like backbone of any exam. Okay, so you can go for any exam. Like previously also, जब मैंने वो XC का questions, XC math, XC exam से पहले हमें XC PYQ solve किया था. Okay, I think some of you were there at that time. Okay, will it be available in IISc library, sir? Definitely it will be available here. Okay, and the book is also, I think, not very costly, some 700, 800 rupees. If you want, you can get a copy. Okay, fine. And maths, so which book? For gate maths. For gate maths, normally, जब मैंने पढ़ा था उस टाइम पे, I have taught maths around so many times. To many of you I have taught actually. I never followed a single book actually, to be honest. I have taken some best points from some of the good books actually. Like for example, linear algebra, I have taken some nice points from Gilbert Strang. Okay, and complex calculus I have taken from Ironman's calculus actually, and then basic calculus I have taken from James Stewart. So there are a lot of people where I have taken some good books and I have given you some points. But normally, if you want to follow a common book, I suggest you. But like again, that will be like more university point of exams. You can go for B.S. Gravel as of now. Okay, B.S. Gravel. Otherwise, yeah, B.S. Gravel is one thing. We have posted some one-shot series initially in the English channel, Wallah English. You can go there also. Okay, fine. So, are you all clear so far? So, shall we proceed from here? Come on, it's already 9:50. We have spent 1 hour 25 minutes almost. Okay. We have still some 40-45 minutes left. So be quick. So please type in the chat box. Is this clear to all of you till this point? Okay. Now let's solve the next question. For one-dimensional isentropic flow in a diverging passes, if the initial static pressure is P1 and the initial Mach number is M1 less than 1, then for the downstream flow, diverging passes, you've got a diverging passes actually. So this is a diverging passes. So let us suppose this is section 1 initially. So somewhere downstream, somewhere here, for example, in the flow, let us see what is the case. Mach number is less than 1. Mach number is less than 1 actually here. Mach is less than 1. Initially at this section, Mach number is less than 1. As I told you, in the last example, in the last class also I was talking about the diverging part of the nozzles actually, rocket nozzles. Okay. So I told you, whenever if Mach number is less than 1, in that last PDF, I have also given this derivation, dA by dV. I think area by velocity around is proportional to A by V times of 1 minus Mach square minus 1. This is the value I think I have given you actually. dA by dV is equal to area by V into Mach square minus 1. I think equality sign directly. No constants. I think this is the relation. Normally I don't remember this. I generally derive this every time. But whenever you see this, you can understand if Mach number is less than 1, this implies dA by dV is negative actually here. Okay, so this implies fluid accelerates in a converging passes. In a converging passes. So here they have given you diverging passes. So this and fluid decelerates. Fluid decelerates in diverging passes because velocity will decrease actually, diverges in diverging passes actually. I have given you this result last time actually in that notes what I have attached actually. If you might have seen, you have all this clear data like Mach less than 1, Mach more than 1. I have given the transitions. So now if you see, velocity will decrease actually clearly because you see this Mach number at the flow is less than 1. So whenever this flow is happening here, then definitely Mach will further decrease. It will come down. Okay. So when Mach number is coming down, that means velocity will decrease actually. So this implies V will actually come down. Okay. When V decreases, now whenever you apply the Bernoulli's equation at this point and also at some point somewhere here, maybe in the downstream direction, you know that here velocity is V1, here the velocity is V2. So definitely V2 is actually less than V1. Now, whenever this V2 is actually less than V1, now whenever you talk about P1 and P2, then if you apply the Bernoulli's equation, you can clearly identify P2. Since kinetic head is getting reduced here, that kinetic head practically gets converted to pressure head. So P2 is actually more than P1 actually. Okay, so this implies velocity decreases and pressure increases actually here. Okay, so this pressure will increase. Clear to all of you? Pressure will increase in this case. Okay. So volume decreases and pressure increases. Let us suppose if they have given you this Mach number at the inlet is more than 1, then if Mach number at the inlet is actually more than 1, then in that case, if Mach is more than 1, then in that case, anyone? So please type in the chat box if Mach number is actually more than 1, then in that case what could be the things? Vice versa, right? Basically your velocity will increase in the diverging passes actually and pressure will come down actually. Okay, so pressure will decrease. Clear? So pressure decreases in that case. I will also I thought of telling you one thing in the last class, but I have forgot. You all know this name ISC, correct? Indian Institute of Science. Excuse me, sorry. Now, if you see IIST, have you ever heard this? Have you ever heard this actually? IIST. Any one of you heard this? You all know this, of course, Indian Institute of Science, top institute, but have you ever heard this? In intermediate, you have heard about it. Good. Of course, yes. For inter students, like whoever is in +1 and +2, this college is a very special college. You know why? Space Tech. Yes, of course. Okay. So this college is basically Indian Institute of Space Technology. Okay. So Indian Institute of Space Science and Technology basically. So if you see, this is like the first of its kind in Asia generally. So I would like to show you some data about this. Why? What is the specialty about this? It was actually started when Abdul Kalam sir was the President of India. I would like to show you some images. That will be in the at the bottom of the Sahyadri Hills. Okay, so the campus will be like amazing. So this will be the campus. Okay, so you can see somewhere here. So these are the Sahyadri Hills at the back. This is in the Western Ghats actually. Okay, so this college is in the Western Ghats, and this college is, you know, this is the basic college actually, and you know, we have very good people came out of that college. Now why this college is very special is actually, of course, you know, this college is very special for BTech joining students actually. If you see, the reason is here in this college, ISRO, Indian Space Research Organization, will directly take the BTech students as ISRO scientists. Like for example, for whatever the equipment you guys are actually struggling now, like you guys are studying and writing the exam, then after interview and then after selection. So instead of that, if you are maintaining some decent CCPA, which is some, I think as of my knowledge, 7.5 around. I'm not sure, but I have to check the brochure. But if you don't have any backlogs and if you try to finish it, ISRO will directly induct you as scientist C. Understood? So that's why this college has very high cutoffs of JEE advanced also. Okay, of course, not the All India rank 1, All India rank 2 go there, but normally at the decent level, whoever has to, basically if they want to work for ISRO, they generally go to this college. Okay, but ISRO don't recruit directly MTech students from here. Again, you have to apply for some specializations. Normally, there are normally this aerospace engineering has 3 specializations: thermal and propulsion, flight dynamics, and flight dynamics, I think. And third one is materials regarding to submit design actually. Okay, so regarding design actually. So we have these 3 specializations here. Normally, you can go to. This is the time to apply. Actually, I think applications might be over by this time. IISc admission, IIST admissions. Yeah, 2023. If you go. IST admissions. Cutoffs will also be very low for gate score. Okay, because the reason is the placements was slightly a bit low, to be honest. But yeah, you can see MTech and Master of Science applications. Applications start from April 6 to May 2nd. So that's finished already. But if you see the specializations and all, I would like to show you just once, because we are talking about ISRO exam. So we should have some things to understand actually. So we have this gate score, actually acceptance of gate mechanical score, of course, not XC. But this college provides you some good understanding, because many times in SDSC, okay, Satish Dhawan Space Center, Sriharikota, and also this, VSSC. VSSC is just beside IIST. Okay, if you see IIST and VSSC, there's also a direct, entrance basically between the two. So you can see that whenever there is some requirement of specialized posts like MTech, thermal and propulsion, or space and flight dynamics. So whenever there are certain special equipments, generally these degrees will help you out sometimes. Okay, because many of you might be feeling bad that you might not have entered a proper college and all because of low gate score, but still this college serves as one of the good option for you. Okay, so anyway, so this is the story. Fine, let us see. This heavy water is used in atomic power plants as. So tell me, what is the answer? Nuclear power plants. So in nuclear power plants, what is the use of this heavy water? Normally D2O. Deuterium oxide. So H2. Normally H2 is for water. D2O is for, like deuterium oxide. So what is this heavy water purpose? Moderator, correct? This is not actually fuel. Normally fuels will be U-238, all these things, chain reaction fuels and all. So source of energy, no, because these fuels, when they bombard with neutrons and all, they release lot of binding energies. Those are the sources of energy. But this is also not used as a lubricant, because in a nuclear reactor, normally there are no moving parts actually, frankly speaking. So therefore, this is actually wrong, but moderator is actually correct. Okay, so moderator is used for slowing down the neutrons. Slowing down the neutrons actually. when these neutrons gets, basically these neutrons actually move with very high velocity. So in that case, they actually moderators are used for controlled fission reactions. If the fission reactions is not controlled, then that's what a atomic bomb is actually. Okay, atomic bomb is basically nothing but uncontrolled nuclear fission. But actually, if you can control the nuclear fission, then definitely this is basically the moderator. It's called the moderator actually in this case. Okay, then let us solve this. A rocket exists exhaust gas with density is equal to 0.5 kg per meter cube out at a 50 centimeter diameter nozzle at a velocity of 1200 meters per second. The thrust is dash. So basically Newton's third law of motion, Reynolds transport theorem. If you apply, you will get the answer. Hi Abhijit. So if you see, so what are the subjects that you actually studied in Bach school? There is a big list actually, but basically, honestly speaking, like not this classical thermofluid mechanics, whatever you study. There is some, I can't reveal the curriculum actually outside, but you can see we study a lot about materials, and it also depends. Like I'm telling you, the course curriculum will not be same at all the locations, because some of you might got recently selected for BRC, the OCES program, okay, orientation course for engineering and science graduates. If you see OCES, we call. So this OCES syllabus is not standardized for every unit of BRC actually. Okay, it depends upon the functionality of the units actually. Like for example, you see NFC, nuclear fuel complex here. So here, since the main point of interest is fuel production, so you will talk about materials, minerals, and basically this all this basic thermo, all these subjects will be there. Maths will be there again. So you have to study a bit of mathematics as well, because all the simulations and analysis, that depends on your mathematical understanding. Okay, and like you see, you study a lot about packing of the materials also. Okay, fine. Sir, I couldn't pass the Bach interview. So that's why basically if you see the syllabus, that syllabus depends upon the functionality of the unit. If you are posted in Mumbai, Bombay, the syllabus will be something slightly different. And if you are posted at NFC, I think this time only two options were given: IGCA, Indira Gandhi Center for Atomic Research, Kalpakam, and the actual means the main head office, Bach, BRC, Bombay. So if you see in IGCA, I think the more course orientation is towards the nuclear reactor physics and all. Okay, you will have RPD divisions and all. So there you will work out. Okay, fine. So let us see. This is 2008, long back when I was almost in 8th class. So let us see. A rocket exists exhaust gases with density 0.5. Rho is equal to 0.5 kgs per meter cube out a 50 centimeters diameter nozzle. So D is equal to 50 centimeters nozzle at a velocity of 1200 meters per second. The thrust is dash. Look, let me talk about the Reynolds transport theorem a bit. Okay, this is open to atmosphere. Now, let us suppose if it's coming out at a velocity V out, and this is coming in at a velocity V in general. And here the area is A out, for example. So this is area out, A out, and this is A in generally. So let us suppose if this is A in, for example here. Then if you see by Reynolds transport theorem, net force acting or thrust, basically you can say thrust force which is generated in this direction is nothing but minus of force acting on this nozzle actually, force acting on nozzle. So this force acting on nozzle is nothing but minus of force acting on fluid. Basically the fluid is exhaust gases here. So now if you see this minus and minus goes out. So what about the force acting on the fluid? Rate of change of momentum of the fluid. So since nozzles has to be under steady state operations, m dot times of velocity at the outlet minus velocity at the inlet. But since nothing is given about the velocity of the inlet, and also practically the inlet velocity will be very less as compared to the outlet velocity, especially in nozzles. So that's why if you neglect this quantity, then you can see m dot can be written as rho A in V in or rho out A out V out. So rho out, this is exits with density. So this is rho out V out square into A out. This is square came basically from this extra multiplication of this V out. Okay, so rho A V square is what you have here in this case. Okay, so rho times A V square. So if you see rho A V square, so F or thrust basically generated is equal to rho A V square. So this is density. So what about density? 0.5 1 by 2 into area of the nozzle pi by 4 d square. So what about diameter? Diameter is actually 50 centimeters. So 1 by 2 meters. So square of that 1 by 4 rho A into area is pi by 4 d square into velocity square. So what about the velocity? 1200 meters per second. So 1200 into 1200. So this value is going to be in newtons. Okay, but the options are actually given in kilonewtons. Okay, so whenever this is in kilonewtons, you put a kilo here and delete these three zeros, for example. Okay, then this is 2 cancels this 60 times and 4 cancels this 15 times. Similarly, this 4 cancels this 3 times. So 3 15s are 45 times of pi actually here. Okay, so this is 45 divided by pi. So if you simplify this slightly, 22 by 7 kilonewtons. So this is almost around 3.5. Okay, so 6.5 around. Okay, because you can see 6 7s are 42 and 5.5 into 7 is 3.5. So almost some 45.5 is there. So 6.5 times of 22. So 6.5 times of 22 gives you 22 into 65, 110. And this is 2 6 are 12 and this is 132 of course. So 1430 with a decimal. So 143 kilonewtons around. Something close to 143 kilonewtons. So if you see 140 kilonewtons. Okay, this difference is because we have slightly, it's 140, but why we got 143 actually here? Because we have slightly overestimated this value. Okay, actually when it is 7, this will be slightly less than 6.5. It will be much close to 6.4 and all. So therefore you can see this value is 140, something close to 140 kilonewtons. Okay. So I am from Shreshth batch weekend. The basic concepts videos of thermodynamics are not fully there. Is it? No, but we have already finished the syllabus, right? Last week, I mean this, I think Wednesday I have taken extra class. It should be there. Maybe you are searching at some wrong space. It should be there. If it's not there, kindly, in the Telegram link, you can talk to me here. As I told you, please message me here. So please message me here, then definitely I will, talk to the team accordingly. Okay, you post your concern, whichever batch, which lectures you are not finding, so that I can, discuss basically. Okay. So please type in the chat box. Is this clear to all of you till this point? Did you basically anyhow? I think for ISRO batch, yes, I am going to take fluid mechanics, and in Weekday batch, I am going to take applications of thermodynamics. So if you wish to, you could join. Then you can take the course. Definitely, we will. Put a brief analysis and in-depth discussion of this Reynolds transport theorem, all these things in the fluid mechanics page. Okay, fine. Or else basically you can join here. Sometimes if you have doubts about these kind of questions, you can post it here. Okay, I'll be happy to answer. So let us see. An aeroplane is flying at a height of 14 kilometers, where temperature is minus 45. The speed of the plane is corresponding to Mach is equal to 2. Find the speed of the plane if R is 287 joule and gamma is 1.4. Actual data. So let us see what is the speed of the plane actually. They have given you height of 14 kilometers, where temperature is minus 45. Speed of the plane is corresponding to Mach number is equal to 2, of course. Okay, so speed of the plane and this gamma. So Mach number is equal to 2, of course. Okay, so let us see. Mach number is equal to 2. So this implies V by A is equal to 2. So actual velocity is equal to 2 times of acoustic velocity. So V is equal to 2 times of square root of gamma RT. So what about gamma? Gamma is how much? Gamma is 1.4 and this is 287. 1.4 into 287 into temperature. So what about the temperature actually in this case? Minus 45 degrees Celsius at that point. So 273 minus 45. So 228 actually here. Okay, so 228 is the value. So 228 is the value actually here in this case. Okay, so let us see what we can do about it. V is equal to, this is in meters per second. This value is coming out to be in meters per second, but these options are given in kilometer per hour. So you multiply 18 by 5. So this value will be coming out in kilometers per hour. Okay, so kilometers per hour, because if you see, if you answered with this 5 by 18, then you could get converted to meters per second. So if you multiply with 18 by 5, this could come out to be kilometers per hour. So let us see. 2 into this is 1.4. So if you approximate this to be 1.414, this could be square root of 2 under. So this is about 2, but 1.4. Okay, let us see. This 228. If you assume this to be around 225, some small value, this square root of 225 would be 15. So 2 into 15 into 1.4 into 287. Let us check what is the value. 287 into 1.4, of course. 2 4 7 are 28, 2 4 8 are 32, 34, 3 2 4 are 8, 9 10 11. So 287, of course. So 8 11 10 4. So 401.8 around. Okay, so this value is 401.8. So if you take this around 400, for example, so square root of 400 is 20. So this is the exact approximate value, because this multiplication is 401.8. So if you round off to 400, and this 228, if you round off to 5, actually here you are decreasing, here also you are decreasing. So the actual value will be slightly large than the value what you get here. Okay, so anyway, if you simplify this, 5 cancels out this 3 times. That's it. 2 3s are 6. 6 20s are 120. 120 into 18. So 12 times of 18 actually here. 8 12s are 96. This is 12 actually. So 6 1 1 2. So 2160 around. Okay. So 2160 kilometers per hour. So you can see out of the options 2179. Yes, this could be the correct answer. Because here you have actually decreased the value. Here also you have decreased the value. So this value what you got is actually slightly less than the more value actually. Okay, so this is 2197 kilometers per hour. So 2160 is what we got basically by small approximations actually. That's why 2160 kilometers per hour is what we have here. Okay, okay, fine. Is this clear to all of you? Did you all understand solving of this question, especially this calculation? Here we have decreased the values. Instead of 228, we have considered only 225. Instead of 401.8, we have considered only 400. So that's why whatever the calculated value, that will be slightly less than the actual value. Okay, so the difference is this 19 out of the 2100. So that value is very close actually. It was 2179 kilometers per hour actually here. Okay, fine. Is this calculation and solving clear to every one of you? Yes. So let us go to the next question. Hydraulic testing of boilers is done at pressures. So as I think this question I have covered in the last class. Okay, if some of you are not there, then you can see this hydraulic testing is basically called this HT. Okay, so hydraulic testing HT. Normally you do HT. I will tell you the procedure for HT because I myself have done this test. You know, got done this test so many times when I was in HPCL. Look, normally how do you do your hydro test is basically, let us suppose if there is a leak at one location for a vessel. Let us suppose there is a vessel, there is a leak at one location. Now you go for the maintenance, you will close that leak. Then after closing that leak, what you will do is you will fill the vessel with water actually, okay, completely, and also at high pressure. Normally how you will fill at high pressure? Let us suppose if the volume of the tank is 1000 liters for example, or 1000 or let us say some 10 meter cube for example. Okay, so let us suppose if the volume of the tank is 10 meter cube. Now normally you can see 1000 10 into 10 meter cube is like the volume. Then 10,000 liters or 10 kiloliters of water is what you can fill. Okay, so instead of filling 10 kiloliters, you will fill some excess water so that creates some high pressure inside the vessel actually. Okay, so within the vessel, when this creates a very high pressure, then we will check whether the device which you have actually done the maintenance will hold that high pressure or not. Okay, and normally the pressure at which you do that hydro testing is almost 1.5 to 2 times of the working pressures actually for any device. It can be boiler or some other devices, it can be some pressure vessels, whatever. So the normal range that you do is 1.5 to 2 times of the working pressures is what we operate them. Okay, I will show you normally some hydro testing equipments. See, this has opened. Okay, this is user registration and all. But here you can see one thing. IST rank list, I think first round of results has also got allotted. Seat acceptance, pay semester fees, IST rank list. I think now everything was very secret, but actual notification. So anyway, I think this is only notification for the MTech programs. Actually, you can see aerospace section based on GATE score only. There is no interview. So these are the 3 branches what I am talking about. Flight mechanics, structure and design, thermal and propulsion. Okay, so you can see this thermal and propulsion is one of the group. So these are the eligible departments with GATE score, everything that was given. valid gate score in aerospace and all. Similarly, we'll have this avionics, and also I think you have mathematics. Yes, maths based on this gate score, and chemistry, of course. Okay, so these are the 4-5 sections. I think physics also you have. This earth, space and science. This is one of the, again, nowadays very recent trends. Even in ISC Bangalore, you have this earth and space sciences section. That's it. Okay, so till 32 years you can apply. Age limit 32 years as on 2nd, 5th. Okay, so till then you can apply for this. Okay, and also you can see normally the cutoffs for the, what do you say, for the interview cutoffs or the final selection cutoffs will be done. So 1.5 times pressure for how many hours? Depending on the criticality of the device, normally for 6 hours, 8 hours, we will hold it. Okay, others? Some equipments might be not very critical equipments. Very critical means, let us suppose even if there is some, of course, we cannot afford any leaks, but even by accident if it happens, still that's okay. Let us suppose if there is a pipe which is carrying water, okay, let us suppose it developed some leak, then you will lose water, that's it, okay, fine. But let us suppose your pipe is carrying petrol, motor speed, MS normal if you call. If it is carrying MS and if that gets a block, if it gets a leak, then definitely that leak is more critical as compared to the water leak. Okay, so therefore every device has its own criticality. Normally you will categorize them as less critical, critical and super critical. So this maintenance will be done as per that. Okay, so let us see. Oh, sorry. Let us solve this. An air conditioned room has one of the walls which is 5 meters by 3 meters of 3.75 centimeters thick brick actually. Okay, so let us see. This is a thick brick, of course. So now you can see here. Right. So let us see. There is a wall like this. Okay. Fine. There is a wall like this. There is a brick actually of some thickness. So what about this thickness? This thickness is again, I think this is a very old question, 2006, long back. Okay. So this is a brick actually. So the air conditioned room has one of the walls which is 5 meters by 3 meters. So 5 meters. Normally length of the wall will be more. So let us suppose if this is 5 meters and this is 3 meters. This is 3 meters actually. Okay, so this is 3 meters. Now whenever you see, this is the condition of 3.75 centimeters thick. So 3.75 centimeters thick. So this is 3.75 centimeters thick. Then let us, the conditioned space is maintained at 27 degrees Celsius when the outside temperature is 47 degrees Celsius. So outside it is 47, means this surface is at 47 degrees Celsius. Outside is at 47 degrees Celsius. This surface is at 47 degrees Celsius. And the inside temperature means basically this value. This temperature inside is how much? This inside temperature is 27 degrees Celsius. So there is a temperature difference, because of which to the air conditioned space heat will flow out from out to in actually. Variation of thermal conductivity with temperature of the wall is given by K is equal to 1 plus 2 into 10 power minus 4 T. K is equal to 1 plus thermal conductivity variation is 2 into 10 power minus 4 T actually here. Okay, so K will be in watt per meter degree Celsius. So that's why this difference can be in per unit Kelvin or per unit degree Celsius. The difference is same, is in degrees, and K is in watt per meter Kelvin actually. Okay, so K is in watt per meter Kelvin. So if you want to convert this, then definitely this T has to be replaced. The heat gained by the conditioned space through the wall. This is actually a question of heat transfer. You can see this is basically a question from the heat transfer actually here. They're just asking you what is the heat flow rate through the one-dimensional conduction. Okay, so basically because of this space present here, there is some conduction of heat inside. Okay, so Q dot. They are asking you what is the value of this Q dot actually in this case. Okay, so let us see. Q dot is equal to minus K J dt by dx actually. Now you can see this can be written as Q dot times dx, or Q dot by A times of dx is equal to minus K times of dt by dx actually here. Okay, so dt by dx. Now you can see when you integrate this basically here, so when you integrate this values actually, so this K is in watt per meter Kelvin, so this T is in temperature. Okay, so whenever this has to be in Kelvin, if you want to write this K here in terms of if you want to treat this in Kelvin, then this K should also be in watt per meter Kelvin actually. So therefore this T, if you convert 2 into 273, if you multiply, K is equal to 1 plus 2 into 273, 576 into 10 power minus 4, so 0. Watt per meter Kelvin actually here. So this is 1 plus 0.576 or 1 into T actually. Okay, so this T is also there. So watt per meter Kelvin. Now this T has to be in oh sorry, I have multiplied actually, sorry. This 10 power minus 4 is 2 into 10 power minus 4 T. 1 plus 2 into 10 power minus 4 T is what you have here, meter Kelvin. So let us keep this in meter per degree Celsius also, no issue. Because K units can be kept like this, no issue. Let us keep that only because temperature difference. This is watt per meter Kelvin because this K is per unit degree difference in temperature. So K can be in degrees Celsius or Kelvin. Now if you integrate this, Q dot is a constant area of heat transfer. So this is 3 by 5. So this is the cross section which I have shaded. 3 5s are 15. So Q dot by 15 times of x2 minus x1. So this is 3.75 into 10 power minus 2 is equal to minus integration. So dx we have already taken out. Okay, so there is no dx here because that dx we have already shifted here. So minus 1 plus 2 into 10 power minus 4 times of t dt. And now you can see whenever x is from here, this temperature is changing from 27 degrees Celsius because you can directly write in degrees Celsius. So 27 degrees Celsius to 47 degrees Celsius. Sorry, 47 degrees Celsius because in the direction of heat transfer. So 47 degrees Celsius to 27 degrees Celsius. So if you do this value, heat transfer, you will get the value of Q dot in some watts actually. What are the units? Watts is given. So let us see. What is the expression actually here? So Q dot is equal to some watts. Let us see what they are asking. The heat gained by the conditioned space. So what is the heat gained by the conditioned space? 850 watts, almost 85 watts and 800 watts. Okay, so let us calculate this. So please calculate this value and tell me what could be the value actually. So please type in the chat box because this calculation you can do actually. So this is 15, 3.75 into 10 power minus 2 is equal to 47 to 27, 1 plus 2 into 10 power minus 4 t dt. This dt will be same when it's degrees or Kelvin, and this, since this value temperature is in degrees Celsius, so we can use the same calculation. Okay, so please calculate and tell me how much you are getting the value. How much value you are getting here? So type in the chat box. Because you can see you have to calculate t square by 2 term actually. Okay, so please will you do this calculation? Yes or no? Because there is one more question, so that's why. So will you do this calculation actually? Normally the temperature difference is 27 and 47 and 15 meter square. 15 meter square is very large value, so it comes I think somewhere around 800 within that range. 800 to 850 somewhere in between that you can do from the calculation. Okay, so please do this calculation because it involves some bit of calculation. Okay, so 47 square minus 27 square by 2, these kind of things. So please calculate this value. Okay, next let us see. In order to burn 1 kg of methane completely, the minimum number of kgs of oxygen needed is dash. Normally if you see the combustion equations under stoichiometric equilibrium, if you have this hydrocarbon CXHY, this requires x plus y by 4 moles of air actually, O2 plus 3.76 N2. This 3.76 will actually come from 78 by 21 because 78% nitrogen and 21% oxygen around. So this 3.76 will come from that equation. Okay, so this is the standard combustion equation for burning of any hydrocarbon. Okay, so you can see this is number of moles. So for 1 mole of carbon dioxide, so for 1 mole of CXHY, this x plus y by 4 moles of this air. So basically that many moles of O2 is actually required. Okay, now they are asking for burning 1 kg of oxygen. Look, for 1 mole you need x plus y by 4 moles of oxygen, correct? You can see here. So what is 1 mole of methane? So here the component is methane. So for 1 mole methane, how many things you need? 1 plus 4 by 4 because methane has this x is equal to 1, y is equal to 4 moles of O2. So 2 moles of O2. So 1 mole of CH4 means 16 kgs of methane gives you, basically 16 kgs of methane needs how many things actually here? 16 kgs of methane needs, this is 2 moles of oxygen. So 2 moles of oxygen. Oxygen molecular weight is 32. So 32 kgs per kilomole. So 16 kgs of methane needs 64 kgs of oxygen. So if you delete this, this is 4. So that means 1 kg of methane needs 4 kgs of oxygen actually for the combustion to be complete, for the complete combustion of oxygen actually here. Okay. This is 4. Basically, this is the standard combustion equation. 1 mole of any hydrocarbon CXHY need this x plus y by 4 moles of O2 plus this 3.76 N2 is basically from the air composition. So oxygen plus 3.76 times of nitrogen is what you have here. Clear to all of you? So please type in the chat box. Is this clear? The combustion equations. Okay, because here they are not worried about the products. They are asking about how many moles of they have given you that methane, and then they are asking about the reaction actually. Okay, so this is the standard thing. So please keep this in mind. 1 mole of any substance actually. Okay, so let me talk here. 1 mole of any hydrocarbon. Any hydrocarbon, like for example CXHY, requires x plus y by 4 moles of air for complete combustion. For complete combustion actually. So this is required for the complete combustion. Okay, so now if you see, therefore since it is methane, x is equal to 4 for CH4, you can see x is equal to 1, y is equal to 4. That's it. So that's what I have done here. Clear? Okay, so this is the standard combustion equation, and depending here we have the products like methane or LPG, propane. If you are burning C3H8, then again according to that you will have the values. Okay, normally majority of your substances what you burn in general, LPGs, all these things are alkanes. Okay, so what are alkanes? Basically this composition CX or CY H2Y plus 2, these are called alkanes. So these are propane, butane, isobutane, all these things are basically the things which you burn in your house. Okay, clear to all of you? So please type in the chat box. Is this clear to everyone? Okay, yes. So let us go to the next question. Okay, so I think these are up to 2006 I think we are discussing. Before that we don't have the papers. Fine. So here these are the questions. So if you have anything to ask about, because I think for ISRO exam, I think this could be the maybe the last time that I may come in front of you. So if you have any things to ask me, you can ask me, all of you, in the chat box. And if you want to access me, as I told you, because some of you might have joined late, so this is the Telegram link where you can get in touch with me. Okay. Clear? If you have anything to ask about the interviews or anything about ISRO, you can put it in the chat box. So my question Telegram regarding the processing of vapor. Sorry, didn't get you. Processing of vapor. Sorry, I haven't seen. But I'll see after this. Okay. I'm also in Vijay batch. Do you recommend again to join ISRO? Look, the difference between Vijay and ISRO, I'll tell you honestly. Vijay is in, completely intended for gate examination. Okay, so the levels of exam are basically the kind of questions that comes will be different. Okay, I'm talking about, like for example, you see, gate is more about analytical, lot of calculations, very in depth of course. Even in ISRO, you should know more. You should have knowledge, but gate is completely analytical. Okay, and Vijay is a long batch. Definitely, we will go to everything in detail, and also so a lot of numericals and all will solve. ISRO is like very crisp theory. Like for example, if you see, we will touch up the concepts very soon, and then we'll just talk about the important points, and then we will start solving some problems actually. Okay, so there's a difference, but anyway, it's on your part to decide. But like ISRO is like a short-term thing which going to happen or which gets commenced within next 55-60 days, so that you will be ready for the examination. Okay. Money, sir, good. Not yet, I'll go and have. Okay. Fine then. Okay, Pritam, Mani, Akhil, Ram, Vijay, Satyajit, Adarsh, Mani. Okay, fine. So thank you all. We'll meet sometime back again, sometime later. Then we will talk about the things. So my question in Telegram regarding the processing of vapor, regarding the equation that contains specific volume instead of total volume in pure substance. Yeah, I have answered that yesterday. Look, the question that you asked is, why we write this actually, okay? Normally in thermodynamics I have told you, of course in paid batches I have told you, sometimes in polytropic process and all. Okay, now tell me one thing. Normally we write the equations in terms of intensive properties so that they can be applied for both open and closed systems. Okay, but these two equations are actually same. The reason is, look, if you write this as mass into V1 whole power n, P2 times of mass into V2 power n actually. Okay, sorry, V2 whole power n. Then definitely P1 m power n, V1 power n, P2 m power n, V2 power n actually. Okay. Okay. You can use anything, but generally we write in intensive terms to apply them for both open and closed systems. That's it. But the equations both are same. Even in case of closed systems, if you apply specific volumes or total volumes, the thing is same actually. Okay, Vijay? Fine. So definitely very soon I think I'll start some course in English channel, Wallah English, but I think we will see that. But we get specific work, na sir? Yes, of course. Normal in case of control volumes, since the mass flow rate is defined, depending upon the mass flow rate, your work output from the turbine changes. Okay, let us suppose in a turbine, if I am earning some 5 kg per second steam, let us suppose. Okay, so this 5 kg per second steam will generate some power. And let us suppose if I decrease my 5 kg to 1 kg, then definitely the total output of the turbine decreases. Okay, but the specific work output will remain the same actually. Okay, if you want to generally talk about the total work outputs, you will multiply with W dot actually. Okay, that's what you have. So is it possible to crack ISRO along with MTech? Why not? When you're studying something advanced, you can definitely do the interviews better. Okay, that's why I have cleared HPCL, BRC, all these things. Fine then. So I hope things are fine, going in a good way. So thank you all. We'll meet soon again sometime later in this channel, and we will talk about the things. Okay. Fine. Thank you all. Then take care. Then I'm signing off for today. Okay. Bye all of you. Take care. Okay. I wish you all the best. Of course, whoever has enrolled for that ISRO batch, I'll be talking about that. If you might have missed that, then definitely I will this is my all the best for your ISRO examination. Thank you all. Take care. Bye.